stunning fireball lights up the night sky over Canada, carrying secrets from the far reaches of space.
When we saw the fireball event on September 25th, I was very excited about it because I knew that there was a distinct possibility of having recovered fragments from it.
Cutting-edge technology makes this meteorite's fall one of the best documented in history.
So we're able to use all of these different techniques to give us a complete 360 view of a meteorite.
Now the race is on to recover fragments, and some turn up in the most unlikely of places.
I heard a loud crash.
Earth's latest visitor could provide answers about the origins of life and the beginning of our solar system.
One of the basic science questions begin. The answer to that may absolutely be tied up in studies of meteorites.
September 25th, 2009. The astrophysics lab at the University of Western Ontario is empty. A lone camera sits perched on the roof, watching the sky. It's one of 7 cameras in the university's all-sky camera network. They are constantly recording to find what they're looking for: fireballs from outer space. At the same time, 100 miles up, a meteor hurtles toward Earth at a blistering 46,000 miles per hour.
As it approaches the Earth, it starts to accelerate as it starts to feel the Earth's gravitational pull. And at that point, everything changes.
Now in gravity's grip, the space rock picks up speed. If the meteor survives the impact, the camera data will allow scientists to mount a search to try and find it. But surviving this journey is easier said than done.
So as the rock comes into the Earth's atmosphere, it's moving something like tens of times the speed of sound. So it's moving 10 or 20 times the speed of a rifle bullet, very, very fast.
Now, 60 miles from Earth and just 3 minutes to impact, the meteor slams into the atmosphere like a ton of bricks. The white-hot rock burns at over 2,000 degrees.
At that speed, the air molecules start to heat the surface. And as the surface gets hotter and hotter, material begins to come off of it. And that's actually what produces the light that we see in the sky as a meteor.
The meteor is now a fireball, and it tears through the atmosphere on a collision course with Earth. Just after 9 p.m., the sky over Ontario lights up. All 7 cameras of the Canadian network capture the burning fireball, tracking its trajectory through the atmosphere. The freshly fallen meteorite could provide important new evidence about the origins of the solar system, and even how life began here on Earth.
Meteorites represent the earliest history of the solar system. We do not have samples elsewhere from any other source that represent that very early first few million years of solar system history. The only record we have of that we can study in laboratories here is from meteorites.
Most meteorites are small pieces of asteroids, the material left over when our solar system formed roughly 4.5 billion years ago.
The ages of meteorites allow us to determine some very fundamental properties about our solar system. They have been samples that have shown us the formation ages of our own solar system. 4.56 billion years ago, the solid matter came together to form these solid bodies. These are messengers to us. They're delivering a wonderful message of what has happened through the history of our cosmos.
So it really gets at origins. It's all about the origin of the Earth, the origin of life, to give us a deeper understanding of where we come from, both in a biological sense and in a physical sort of earth science sense.
Meteorites fall to Earth every day, but with 2/3 of the planet covered by ocean and most of the land uninhabited, they are rarely found.
In order to have any sort of reasonable prospect of recovering a meteorite from a bright fireball, you need to monitor a huge area of the Earth or monitor a small area in the atmosphere for a long period of time. So typically, camera networks are set up, they have to be able to run for years or decades to have any sort of chance of recovering one meteorite from one fireball.
Planetary scientist Peter Brown operates the University of Western Ontario's all-sky camera network.
This is one of the 7 cameras in the network. So on the night of September 25th, the cameras were running. It was about an hour or so after dark, and there was a very bright fireball that from this particular camera was seen to come in roughly like this. We're actually covering somewhere in the neighborhood of about 100,000 square kilometers with the network. Each camera is seeing out to, say, 300 or 400 kilometers from the actual camera position. So we're covering a lot of southern Ontario, part of the Michigan, Ohio, and certainly all of the Great Lakes.
But this network also uses sound and radar technologies to watch the skies.
So that's something that is very unique in the world. There's no other network that combines all those technologies to look at meteors, a single meteor, using all of those different techniques.
Radar detects the invisible trail of electrons that the fireball leaves behind. And infrasound sensors detect the shock wave that it makes as it tears through the atmosphere.
Our real science goal is to try to observe events in great detail with each and then by looking at the event from all of these different angles, piece together a complete reconstruction of its initial mass and its initial orbit, how it broke up in the atmosphere.
There are 4 infrasound stations that picked up the September 25th fireball.
By having 4 elements in the infrasound array, we can figure out where the source is coming from, and also we can figure out what is the apparent sound velocity that approaches the infrasound array.
Elizabeth Silber and Zbigniew Szymanski are part of Peter Brown's team and help maintain the infrasound installations.
This sensor has the purpose to register very tiny pressure waves in air. These are usually below the human hearing range.
This infrasound device can pick up low-frequency sound from everything from shuttle launches thousands of miles away to lightning storms and even Niagara Falls.
So we're able to use all of these different techniques to give us a complete 360 view of a meteor. It gives us a huge amount of information, an awful lot of data about each event that enters the atmosphere.
In all, the Fireball Detection Network consists of 7 all-sky cameras, 4 infrasound arrays, and 6 radar stations. They're watching the skies around the clock, searching for Earth's next visitor. On the night of September 25th, these devices record the fireball event, collecting an unprecedented amount of data.
We're actually really fortunate. We've only been running this network for 4 to 5 years, and we sort of won the cosmic lottery in some sense because of that one event.
Initially, what we needed to do was to work out what the trajectory was through the sky and work out what the possible fall locations on the ground were.
Peter Brown and his colleague Phil McCausland begin to pore over the data from the Ontario fireball. Their goal, to calculate where it came from, where it may have landed, and mount a search to find it. The meteor first became visible to the all-sky camera network when it turned into a fireball through a process called ablation.
When a rock arrives at the Earth's upper atmosphere, starts entering and starts really slowing down, the main process that goes on initially is the material gets stripped away from it.
The rock literally vaporizes from the intense heat.
We see it as a trail of sparks flying behind the main fireball. It's just little bits and pieces getting stripped off and becoming independent little fireballs.
cameras captured the entire process.
We're seeing feed from each of the cameras from the network. Each of the cameras is pointed straight up. What you're seeing here is an image showing the entire sky. So right in the middle is directly overhead as seen from the camera site. And around the sides here, you're seeing the horizon. The fireball actually passed almost directly over the camera. Very fortuitous, just the geometry was just right.
Capturing the fireball's descent from multiple angles enables Brown to pinpoint its exact location.